In this lesson, we're looking at velocity and acceleration for motion along a curve. So essentially what we're looking at is displacement, velocity, and acceleration vectors. So if we consider a displacement vector, rt is equal to xt in the I direction, yt in the j direction, and zt in the k direction, and we think of this as a position vector, in other words, a vector representing the change in position over time, then it follows that in order to find a velocity vector, we would need to consider dr dt, or r dot, as our velocity vector. So finding the derivative of this original position vector allows us to consider the velocity at any point in time. If we then take one further step and we consider acceleration, where acceleration is the second derivative, so d squared r over dt squared, or r dot dot, the second derivative, we know that by finding the second derivative of that position vector, or finding the derivative of the velocity vector, we'll be able to find the acceleration vector. So really our focus this lesson is the relationship between displacement, velocity, and acceleration, in that if we have our displacement, we can find the velocity by finding the derivative with respect to time. Now to get your acceleration, again, we find that derivative with respect to time. So this is technically velocity and this is technically acceleration. Now if we wanted to go backwards from acceleration to velocity, we would have to find the integral with respect to time. And if we wanted to go back again from velocity to position, we would have to find the integral with respect to time. So this little relationship here allows us to jump between displacement or position, velocity, and acceleration using differentiation and integration, so using calculus methods. Okay, so we're going to apply this. We'll build on this through the next couple of lessons, and we'll end up looking at projectile motion and circular motion. But today we're just looking at quite simple scenarios. So the first example pulled directly from the textbook gives us a position vector. Now we're including exponentials, so the differentiation is slightly more complex. So we're given a position vector, and for part A, we're trying to find the velocity vector, part B, the acceleration vector, and then part C, we want to find the speed. So when we consider the velocity vector, we know that the velocity vector is going to be this r dot. And to get that, we're looking at dr dt, the derivative of that original function. So first of all, when we find the derivative in the I direction, we have e to the power of t. The derivative of e to the power of t is e to the power of t. We then have 2/9 e to the power of 2t, so that derivative is going to be itself, but multiplied by the derivative of this power here, 2t, so multiplied by 2 in the j direction. And we can tidy that up to say that our velocity vector is going to be e to the power of t I, and 4/9 e to the power of 2t j. Now part B, we're looking at the acceleration vector, so we're looking at r dot dot. So we're looking at dr dot, so the derivative of r dot with respect to time. So we're finding the derivative of the velocity. So in the I, the derivative is going to be itself again, so e to the power of t in the I direction. And when we find the derivative of that 4/9 e to the power of 2t in the j direction, again, we're going to multiply by the derivative of this bracket, or the power, because it's a chain rule. So we're multiplying by 2. And we end up with e to the power of t in the I direction, and 8/9 e to the power of 2t in the j direction. So here's our velocity, and here's our acceleration. Now part C, we're looking at the speed. So speed is going to be the magnitude of the velocity vector. So magnitude of e to the power of t squared and 4/9 e to the power of 2t squared. So this becomes a relatively simple algebraic problem. This is e to the power of 2t, and we have 16 on 81 e to the power of 4t. Now, of course, this will be dynamic, but that's still our answer, and that'll be in meters per second. So speed can be calculated by substituting in the t value for any time. Okay, so we'll look at a second example. In the second example, again, directly from the textbook, we've been given a vector function in 3 dimensions where t is greater than or equal to 0. Initially, it wants us to find the velocity of the particle at time t. So we're looking for a velocity function. So we're looking at for r dot, and we know that's going to be dr dt. So we're looking at the derivative of each of these components separately. So the derivative in the I direction, derivative of 2t take t squared, is going to be 2 subtract 2t. The derivative in the j, derivative of t squared take 3t, will be 2t take 3. And then finally the derivative in the k direction, derivative of 2t, is just simply going to be 2. So there we have it, there's our velocity function. For part B, we're looking for the speed of the particle at time t. Remember that speed at any point in time is going to be the magnitude of the velocity vector. So the magnitude of the velocity function will be square root of 2 take 2t all squared, 2t take 3 all squared, and 2 squared. So expanding those binomials, we get 4 subtract 8t, add 4t squared, add 4t squared, subtract 12t, and 9 plus 4. So we end up with 8t squared, subtract 20t, and add 17 meters per second at any point in time. Now, part C asks us the minimum speed of the particle. So if we're trying to find the minimum speed, we're looking for when the derivative of the speed function is equal to 0. Alternatively, we could look at it as a function and look for the turning point. I'm going to use this approach. Now, because this is a parabola within that square root, when the parabola is at a minimum, the entire function is at a minimum. So I'm going to say that to find the time t when speed is a minimum, I'll look at the derivative of speed squared. And so I'm looking at the derivative of 8t squared, take 20t plus 17. We get 16t take 20, let that equal 0. And 16t is equal to 20, and then finally t is equal to 20 on 16, which is equal to 10 on 8 or 5 on 4. Now to find the actual speed, we're going to put that 5 on 4 back into the speed equation. So our speed will be equal to square root of 8 multiplied by 5 on 4 squared, subtract 20 lots of 5 on 4, and add 17. So we have square root of 8 times 25 on 16, subtract 20 times 5 over 4 and 17. The 8 and 16 will cancel down, so this becomes 2, and that's 1. So we have 25 on 2, 4 will cancel down to 5 and 1. And so now we have, so that simplifies to 25 on 2, subtract 25 plus 17. So we have 25 subtract 50 plus 34, all on 2, which leaves us with 9 on 2. And that leaves us with 3 over root 2, or 3 root 2 on 2 meters per second as the minimum speed. And this occurs when t is equal to 5 on 4. Okay, so depending on whether you're calculating that out, you have to be careful there and not make any numerical errors. If that's a calculated job, there's multiple different ways to do it. Alright, so we'll look at another example. Okay, so in example 3, we're looking at the possession of a projectile at time t, and so it's given by 400I plus 500t take 5t squared. That's when t is greater than or equal to 0. So it initially asks us for A to calculate the time taken to reach the ground again. Now this is where we can start to think in a compartmentalized manner. So for it to reach the ground, we should be able to logically come to the conclusion that the vertical height is equal to 0. Now if we can use that, that means we're saying that the vertical height, or that vertical position, so RV is 500t subtract 5t squared. And as we're looking at that when it's equal to 0, we end up with something that's going to be a relatively simple solve. So common factor here is 5t. We're left with 100 subtract t. And using null factor theorem, we get t is equal to 0, or 100 take t is equal to 0. So we end up with t is equal to 100 seconds. Now it's not going to be this, that's going to be the initial time. So the time taken to reach the ground again will be 100 seconds. Now when we look at part B, we're trying to find out the speed at which the projectile hits the ground. So we're looking at the magnitude. Speed is going to be the magnitude of the velocity vector. So we'll start by finding the velocity vector. And so we find the derivative here. It's just going to be 400 in the I direction. And in the j direction, we will have 500 subtract 10t. And so therefore our speed will be the magnitude of that. So it's 400 squared plus 500 take 10t all squared meters per second. Now because we're looking for at the speed specifically when the projectile hits the ground, we're looking at when t is equal to 100. So our speed will be square root of 400 squared and 500 subtract 10 times 100, so that's 1,000 squared. So we end up with 400 squared plus 500 squared. So if we take out that common factor of 100 squared there, we get 100 square root 4 squared plus 5 squared, which gives us 100 square root 41 meters per second. So this is a speed as it hits the ground. When we look at part C, the maximum height of the projectile. So again, this is a logic thing. If we can consider something up into the sky, at this point here, the vertical velocity is 0. So if we look at the vertical velocity being equal to 0, we can say that the vertical component of the velocity is 500 take 10t. So when we let that equal 0, we get 10t is equal to 500, and therefore the time it takes is going to be 50 seconds. If we're trying to find the max height, we're going to put that into the vertical component of the position. So that's going to be 500t subtract 5t squared. So 500 multiplied by 50 subtract 5 by 50 squared is 25,000 subtract 12,500, which gives us 12,500 meters high. Now finish off this last one asks us for the initial speed of the projectile. So the initial speed means we need to consider the entire vector and then find the magnitude. So we're looking at r dot 0. So putting that in, it's going to be 500 and then 500 in the j. So 400 in the I, because we found that derivative earlier. 500, take away 10 times 0 in the j. We end up with 400 in the I and 500 in the j. And so that initial speed, so speed 0, is going to be square root of 400 squared plus 500 squared. So that'll be the same as the landing speed, which ends up being 100 square root 41 meters per second. Okay, so we could continue doing examples. As long as you understand the process here, calculus allows us to easily convert between position, velocity, and acceleration. And when we start applying these scenarios, we need to consider logically which part of the components we can apply. All right, so that concludes the lessons on velocity, acceleration, and position.